I'm Dr. Roger, and today we're looking at differential equations, not SAT. And in particular, we're looking at systems of first-order linear ordinary differential equations and the relationship between those systems and second-order ordinary differential equations. So I can take this equation, I'm going to write it as a system of first orders and solve using eigenvalues and eigenvectors. I'm going to do that by saying let x1 equal y. So x1 prime equals y prime. I'm also going to let x2 equal y prime. So x2 prime equals y double prime. And since x2 is y prime, that's x1 prime. Substituting these into my original equation, y double prime is x2 prime. And I have plus 8. I can either call this x2 or x1 prime. And I'm going to call it x2 because I only want one prime in each of my first order linear ordinary differential equations. And then minus 9x1 equals 0. And I also have x1 prime equals x2. And I can rewrite these as x1 prime equals 0x1 plus 1x2. And x2 prime, moving these terms to the right-hand side, equals 9x1 minus 8x2. This can be written in matrix form as x1, x2 vector prime equals 0, 1, 9, negative 8 times vector x1, x2, or just vector x prime equals A times vector x, where matrix A is 0, 1, 9, negative 8. And typically we'll solve the system of equations x prime equals ax, where A is a specified matrix. And I'm hoping when I solve this, I'll get something that's connected to, we know the solution of this guy from the characteristic polynomial. If we substitute y equals e to the rt, that gives us y prime equals r e to the rt, and y double prime equals r squared e to the rt. So r squared e to the rt plus 8r e to the rt minus 9e to the rt equals 0. E to the rt times the characteristic polynomial r squared plus 8r minus 9 equals 0. The exponential is never 0, so I can divide by that. Factoring r and r, 1 and 9. The 1 is negative and the 9 is positive. And if a product is 0, either the first factor is 0 or the second factor is 0. So r equals 1 or r equals negative 9. This gives us y equals e to the 1t or y equals e to the negative 9t. Our general solution is y equals c1 e to the 1t plus c2 times e to the negative 9t. And we're hoping that the solution we get from systems of equations will somehow be connected to that. In the real world, we would be unlikely to rewrite a second order as a system of first orders because the matrix methods aren't as fast as our characteristic polynomial when we're dealing with quadratics, because we're really good at quadratics. If we're dealing with a very high order polynomial, a system of equations for a multi-story building where we might have a polynomial of degree 100, I don't want to work with degree 100 in a polynomial. Computers are great with matrices, so I'll rewrite that high-order system, high-order differential equation as a system of first-order differential equations, write as a matrix, and let my computer solve the matrix equation. So one of the primary purposes of these is to turn high-order polynomial equations into systems of first orders that can be solved with matrices. another purpose, of course, is situations that are genuinely systems of equations as presented. So we know that to solve, we're going to want eigenvalues, and eigenvalues come from the determinant of your matrix A minus lambda times the identity equals 0. So I have 0, 1, 9, negative 8 minus lambda times 1, 0, 0, 1. And I want the determinant of that, which is determinant of negative lambda, 1, 9, negative 8 minus lambda. And that determinant is supposed to be 0. The determinant of 2 by 2 is the product on the main diagonal minus the product on the off diagonal. So that would be lambda squared plus 8 lambda minus 9 equals 0. And that is the characteristic polynomial we saw before. The 1 is negative and the 9 is positive, so either lambda minus 1 equals 0, so lambda equals positive 1. I'm going to call that lambda 1. Or lambda plus 9 equals 0. Lambda equals negative 9, and I'm going to call that value lambda 2. Now for our first eigenvalue, I want A minus lambda times the identity, so that would be negative lambda, so that's negative 1, and then 1. 9 and negative 8 minus 1 is negative 9. And I want that times some vector. I'm going to use the Greek letter xi. It's pronounced as a K followed by an S, and then your vowel. So xi. I'm going to use xi because of tradition. Xi1, xi2 equals 0, 0. And we can't use x because x is our solution, and the eigenvector is not an actual solution. So we need a different letter, and you will commonly use xi in a variety of applications in differential equations. So I'm following many of our textbooks that use xi there so that we can get used to it. And when we multiply the first row, we get negative xi1 plus xi2 equals 0, or xi1 equals xi2. And the second row gives us an equivalent equation, 9xi1 equals 9xi2. You can't solve this uniquely, but we can choose, and I'll choose xi1 equals 1. That means then xi2 is also 1, and our eigenvector, I'll give it a superscript of 1, is a vector 1, 1. I do superscript rather than subscript because subscripts are normally components. Now let's look for eigenvector 2. Eigenvalue 2 is negative 9. So A minus lambda I is minus lambda is positive 9. 1, 9. Negative 8 minus negative 9 is negative 8 plus 9 is 1. Times xi1, xi2 equals the 0 vector. And those are exactly the same equation. 9 xi1 plus xi2 equals 0. If I choose xi1 equals 1, then I have 9 plus xi2 equals 0. So xi2 equals negative 9. And my second eigenvector is 1, negative 9. Now in some applications, and you may encounter this in linear algebra or for example multivariate statistics and some others, in some applications they will ask you to find unit eigenvectors, so we will normalize these. If you take the sum of the squares of the components, that would be 1 plus 1 is 2, square root is root 2, and this vector over root 2 gives you a unit eigenvector, and similarly here, this vector over root 82 gives you a unit eigenvector. In some applications, eigenvectors are defined to be unit vectors. You should always pay attention when a new subject area introduces eigenvectors, so that if we have an implicit requirement that they be unit vectors, you become aware of that and use that. Now that I have these eigenvectors, let me erase this part so I have some board space. My solution is going to be vector x, which is the solution, is c1 e to the lambda 1 t eigenvector 1 plus c2 e to the lambda 2 t eigenvector 2. So that would be x vector is c1, lambda 1 is 1, so that's e to the t, times eigenvector 1 is 1, 1, plus c2 e to negative 9t times 1, negative 9. That's x, which is x1, x2, equals c1 e to the t, c1 e to the t, plus c2 e to the negative 9t, negative 9 c2 e to the negative 9t. x1 was originally y, and x2 was originally y prime, and that's c1 e to the t plus c2 e to the negative 9t, and c1 e to the t minus 9c2 e to the negative 9t. And if you look at just the first row of that solution, that is my solution from the characteristic polynomial. In many cases, you're just looking for the x1, and that will be your first row. In other cases, we're interested in this form here. And if our problem presented itself as a system of equations rather than as a higher order equation, we would stay with this solution because that is the solution in the context that the problem was presented. This is an initial introduction to solving systems of first order ordinary differential equations by using eigenvalues and eigenvectors. It's well worth polishing your skills on this topic before you move to anything more advanced. Repeated eigenvalues are more intricate, and complex conjugate eigenvalues are also a challenge, and I'll look at those later. Come back soon for my next video. With differential equations, there's always more.